All right, so maybe let's get started. We have, for first group up is Carlos, Alex, and Sam talking about CPS passwords. So Sam, go ahead.
I'll take it. Thank you. So our project was on password management security, and specifically we designed an app to try to make it easier for users to adopt a mental password management scheme. Next slide, please. So basically the problem that we're dealing with is that most users have over 20 accounts that they need passwords for, and humans just can't remember more than 20 strong passwords. So this encourages bad practices like using extremely weak passwords that are easy to remember and reusing your password over multiple sites to reduce the memory burden. So one solution to this that is really pretty good is a password manager, which is basically an application that stores all your passwords in encrypted form, encrypted with some key that is basically a master password that you have to remember. And this is really pretty good, but there are a couple of small issues. One is that you basically have a bunch of really sensitive password information that's guarded by a master secret that you have to use on your computer fairly frequently. And so this makes it possible for an attacker, if they can steal that information, the encrypted information, and the master password, then they can get onto all your sites. And that's a pretty devastating possibility. And then the other problem is that you're dependent upon a single application, that password manager, to retrieve your passwords. And so if for some reason you can't access it, that is also pretty bad because you can't get into any of your accounts now. So one alternative to a password manager or a computer password manager is a mental password management scheme. So there's this idea called QPin Select that was developed by these folks in 2018. And the idea is that you should be able to store all the information required in your own personal memory. So you don't need to write anything down or store anything on a computer. And this means that you aren't dependent on any device or application for your passwords. So the mechanics of the idea, you pick a long passphrase. I think it's supposed to be over 36 characters long, so a bunch of words, and a 4-digit PIN. And you just have to remember those. And then for each website you want to make a password for, you pick a 4-letter Q. So the classic example for Amazon, it would probably be AMZN. And then the QPin Select scheme is really an algorithm to deterministically compute a password from your passphrase, the PIN, and that 4-letter Q. And the idea is that you should be able to do this mentally so that you don't need to write anything down. The mechanics of the algorithm aren't really that important, but you're basically going through your Q letter by letter and your PIN digit by digit in 4 phases to select 3-letter blocks out of your passphrase, and you end up getting a 12-letter password that's pretty strong. Now I'll pass it off to Sam.
Okay, so the real reason we made the CPS app is to get users off the app. So it's not a great business model, but the idea is we want users to use this app to understand how the CPS scheme works and then be able to transition to doing this mentally. I think one of the biggest obstacles or barriers to entry of users taking on a mental password scheme is that it's really tough to do the first couple times. And so this app is designed to help users get over that bump. Now, why is CPS better than the traditional ad hoc password scheme? And by the traditional ad hoc password scheme, I mean you're signing up for a new service, they ask you to enter a password, and you most likely enter a password you've already used before or a weak password. And that leads to a couple different threats. The main thing is credential stuffing, which is where if I reuse a password and that password is stolen, the attacker can try and stuff that into my Gmail, my bank account, and all my other online services and try and get access. Whenever I use a weak password, that's really susceptible to just the attacker guessing the password or to that password being cracked if that service is breached. CPS allows us to deterministically generate a new password for each online service because each online service has a different queue. And furthermore, each password is of sufficient entropy. It's 52 bits of entropy. So the idea of entropy is essentially 2 to that number is how many guesses the attacker would have to do before they guess that password. So 2 to the 52 is a pretty large number. The attacker would have to work pretty hard to try and guess one of these 12-character passwords. And the last thing we really wanted to hit on is why this is better than a password manager. So in January, LastPass, which is what I use, had a major outage. Luckily, I wasn't affected, but a lot of users basically for about 3 or 4 days couldn't access any of their passwords. Now, if you're like me, I basically randomly generate all my passwords using the password manager. So I can't get any of my passwords unless I have access to LastPass. The great thing about CPS is every password is deterministically regenerable. So as long as I remember my passphrase and my PIN, and I can reasonably guess the queue because, for any online service, there's only a couple of queues that it could be, I'm able to regenerate my password. So with that, I'll pass it off to Carlos to kind of walk us through this video of how the app works.
Yeah, so this is just a video of the currently implemented features. So what you see here is the screen when you first are going to set it up. It'll prompt you to create a PIN. And after that, we'll move to getting your passphrase. You have the option of either typing one in, or you can use the handy generate passphrase we put in here. And you can go through a couple until you get one that you like, or you can modify it to your liking. Once you've got your password, your passphrase, you set up an everyday password. This is just for use with the app while you're getting used to the scheme, and this will make it lower the burden of entering your PIN and passphrase each time. So once you've entered those 3 pieces of information, it'll be shown to you so you can write it down or set it up however you need to use. And then you can start using it. This is the main screen where you set up to get a password. So in this case, I'm going to create a password for my Microsoft account. I choose the PIN, the QMSFT, and I'll be prompted to enter some extra information about this password that I'm generating. So the service name is Microsoft. And in the case where the length requirements would conflict with normal CPS usage, we've created a way so you can modify the way it works. So this will help the app do it. And there's also instructions so that you can do it yourself. And you're also going to put in an allowed special character because different sites might have different special character requirements. So once you've confirmed that, you can see the generated password, which includes capital letters, a number, and the special character. And then thereafter, when you enter the same queue that you've already set up, you'll be taken directly to the password generation. We've also implemented some features to help get users in the direction of using this themselves. Well, first are the convenience features, resetting your password based on current password. And you're also allowed to reset based on PIN and passphrase because that is, after all, the underlying secret information. And as long as you have that, you should be able to keep using the app. Of course, you can view the PIN and passphrase in case you're going to, for example, change devices. And then the last 2 features are the most important toward learning how to use the scheme. So view queue information lets you look up a queue or service name and see underlying length requirement and special character requirements in case you should need those while deriving the password yourself. And finally, and most importantly, manual retrieval instructions. And here we put together step-by-step instructions so that you can do the derivation yourself. And this also includes the special character and length requirement cases. So you'll know how to do those as well. So that theoretically, after a certain amount of time of using the app, you would have this process memorized and you would be able to stop using the app and just use the information inside of your head along with the length requirements and special character. So that's it as far as the current app.
I guess you guys got one question from Max on the chat, whether you guys have actually used this for new accounts.
I've actually set this up for a couple of my accounts.
Yeah, I haven't started it. I guess another barrier to entry is that it only really works if you kind of migrate all your passwords to it. And I haven't taken the time to do that yet.
So for the second question, that's one of the strengths. And they do a more in-depth analysis in the paper. But basically every change we've made has only added entropy. So they argue in the paper that given a plain text attack where an attacker has one or more of the passwords, there's still great difficulty in deriving other passwords.
For the question about the app security, we basically use the same, or we tried to use the same kind of encryption methods that a password manager would use to store the passphrase and PIN guarded by the everyday password. So from that perspective, the app is hopefully about as easy to crack as a password manager. Of course, the idea is that the app, in the long term, the app wouldn't need to remember any really secret information because you'd be able to do it in your head. And that's the real strength of QPin Select.
For the paper that this is based off of, it's based off of QPin Select, a secure and usable offline password scheme. I'll post a link to that in the chat right when we're done.
All right, any other questions? All right, thanks very much. I guess yeah, thanks for the presentation. Seems cool. I guess next up we have Robert talking about reverse engineering. Do you want to pull up your screen if you want to?
Yeah, let's see. All right. So for my project, I had some adventures in Android reversing. And this is like a proper adventure where you sort of start, you don't really know where you're going, but you go somewhere and it ends up being interesting. So yeah. The goal of this presentation is just to give you guys a general sense of like how modern Android anti-analysis techniques work, and like what are some ways you can think about like what they perform well against, what they perform poorly against, how you can get around them, so on and so forth. So the app that I choose to reverse, I won't say specifically which one it is, but you know, it has like 5 million downloads. It's a game. And after some digging, it looks like it's protected by this nprotect AppGuard thing, which looks like it's also used for like fintech apps, like banking stuff. So I think it's like a pretty good, probably like a pretty good indicator of what like good Android anti-analysis looks like in the present day. All right, so the first thing, you know, you get an Android app, you're thinking about like reversing it, figuring out what's going on. You know, Android apps are built with Java, so a reasonable question is like, oh, can we just reverse this thing into Java? And the answer is that you can, but if the people on the other side have used a good packer, what you get is something that looks like this. And so you can see that like everything is generated through reflection, right? So like you create classes with like class.forName, and then you can't even tell what the reflection is doing because the strings that create the reflection are obfuscated. So if you think like, oh, this is actually not that bad, right? Because we can just take this string and take a look at how they're deobfuscating it and then do that ourselves, then reflect everything ourselves and then run the app. If you look at the function that does the deobfuscation, at first it looks pretty standard, right? You've got like a loop, some bit shifts, some other like garbage, but like nothing too bad. But a super interesting technique is that they seed this deobfuscation function with the result of a stack trace. So like presumably it's super annoying to manually figure out what a stack trace is going to look like when this thing runs. So this is a really like snazzy way of hiding a key in an application where like the whole source can be known. I think this is a really slick trick. But I also don't want to like manually figure this out. So this is like the end of static analysis for me, and we're going to start looking at dynamic analysis. So our tool of choice is Frida, which claims to be like a world-class debugging software for Android. It is actually pretty good. And the way that it works is you write this like Python script, and basically the Python script, you need to have a rooted Android device, and you put like a server executable on the device. Then you tell the server to please run the application. You attach the application and you inject some JavaScript, surprisingly. And then you resume the application and you get to see the results of your script. So like super basic script looks something like this. You can say like, oh, like please tell me the classes that are loaded, do it synchronously and print them out. This is not super interesting, but it's actually, it's pretty useful in terms of getting a sense of like what classes the app is actually loading. Like from the static analysis, you can't tell anything about what the app does. So the more interesting examples are like, like let's try to hook like libc's open, right? And see like what this app is really getting up to. So you can say, oh, like let me find where libc's open lives. Here's its signature, so we can parse like the C arguments into JavaScript, and then we replace the function with something that prints out the path and then calls open. So it'll basically be transparent to the application, except for the fact that a pointer will change, and we'll get to see as the app called open, what it was trying to open. This is one of the old like sounds good doesn't work. And the reason it doesn't work is because the application, when you run it with this setup, like 15 seconds into running, it tells you there's a security policy violation. And so this is like super big, right? Like what does a security policy violation mean, right? Like it could mean that the app knows that you're on a rooted phone, or that it's connected over USB, or like God knows what. So the game here is to try to think up some Java function that you can hook to get an idea of like what's actually going on and why you're getting this security policy violation. So I think this is actually a fun problem if you want to take some guesses or like have some ideas about what functions are potentially interesting ones to hook in a situation like this. Let me see if I can pull up the chat. All right, so unclear if people have ideas or not. I think good functions to think about are ones that you can be like pretty sure that any app is going to call. It's going to call with arguments that you might actually care about knowing. Like they'll give you sort of a feel for what's going on. Super good ones are stuff like string builder. Like if you hook string builder, you get to see like every string that the app builds. And especially in an app that relies so much on this like reflection stuff where you have to construct these strings on the fly, this is super useful. Did you ever try to hook functions with the exposed framework? Okay, yeah. So I think exposed and Frida are competitors. I didn't look into exposed super closely, but anyway. So if we look at one of the string building functions and you hook it and you look at the output, you get like thousands and thousands of strings that are built. But it turns out that one of the strings is this Tamaka for business, which says it detects an invalid libc SO and then all this other stuff. So what we can figure from this is like, oh, the app must be checking the integrity of the libc file that it's, the libc shared object that it's loading in. So somehow we have to get around this. Natural thing to think is like, oh, can you patch the integrity check somehow? Like, can you, presumably it's getting hashed. Can you patch the hashing function to like always return 0? Or even like, can you patch the final equality check where the result of the hash is compared against like what it should be, and just have like byte string or byte array equality always return 0? And it turns out that neither of these things work. And so there are also no like super suspicious library calls. And so you sort of think like, oh, like how could it possibly be that we're doing hashing, but we're like not calling any clear hashing functions, and we're not checking equality of bytes? And you sort of realize like, oh, what must be going on here is this hashing is getting done in native code. It's not actually getting bubbled up to Java where we can hook it easily. And so the game, of course, is like you have to find this function where the hashing is happening, and it's not obvious at all where that is. But one of the ways we can think about finding something like that is with ptrace. So if you, for people that don't know, ptrace allows you to like, basically allows you to like see what an app is doing. It's a Linux system call. But if you run ptrace, you find out that the app forks twice, and that you can't actually ptrace anything. And the reason, the way that you as an app prevent ptrace is you ptrace yourself. And so when you look at this app, there are 3 processes going, and presumably what's going on is there's some sort of ptrace chain where they all start and they all ptrace each other to make sure that you can't ptrace anyone. So yeah, you're in a bit of a tough situation now, right? You have an app that won't do anything interesting if libc is hooked. And the code that's checking whether libc is hooked or not is in a native routine that's annoying to find. And you can't find the routine with ptrace because the app ptraces itself. And if you try to hook libc ptrace, for some reason this hook just like never gets called. So I think they're doing some interesting, I think they have some interesting way of calling ptrace. I don't know exactly what it is, but I'd be interested if people have thoughts on this. Yeah, so sort of wrapping up here, the one thing that you can always do for this stuff is you can always go into kernel lands. So you need to recompile your kernels. All the kernels are under GPL, so you can find the exact one that runs like your old phone. You can get them either from Samsung or the modding community, and with like a ton of patience and a ton of kernel recompilations, you can in fact just like rebuild the kernel. So if you do that, you can try to like patch ptrace to like a fake work, like return 0 if you're not root and actually work if you are root. This really seems like it should work, but it turns out that it doesn't because the app like must be doing some more involved check to see if ptrace works or not. So finally, like the boring solution here, right, is that you control the kernel, so you can really just like do whatever you want. In particular, you can compile the kernel with support for procmem and prockmem, and like dump memory to file, or you can compile it with support for linked kernel modules and link in a kernel module that allows you to dump memory to file. And then you can bin walk the result to get the memory of the app. This is like not a great solution, and I'm kind of sad that like this is what it comes down to. I was really hoping to get a ptrace, but yeah, it's a good reminder that if you control the kernel, you can do whatever. Yeah, so that's sort of all. I'd be interested if people have questions, comments, thoughts. Yeah.
So were you able to make progress on understanding the example app you picked in reversing something out of it that you were aiming for?
Yeah, so I think like the boring answer here is you can extract like assets, right? From you can extract assets, which is like fine, not super interesting. Presumably this, I didn't have time to like look super carefully through this memory dump, but like you can be super sure that if you dump the memory from, like if you dump physical memory while the app is running, for sure you got any code that the app happens to be executing. Wasn't super interested in like getting into like debugging like the final like classes.dex or whatever comes out of the memory dump. But yeah, I think this is like yeah, I think there's nothing where it's like, oh, like this app is like doing this awful like encryption scheme, or like they just made this awful mistake. I think it's an example of like an interesting app that's clearly doing this stuff pretty well, and it's interesting to see like what state-of-the-art Android anti-analysis looks like.
All right, thanks very much. So I guess
Yeah.
that's probably it for to make sure we have time for other groups. So yeah, thanks for telling us about that.
Yeah.
So next up we have Max, Alex, and Max, Alice, and Sule. I'm not sure which one of you guys is presenting.
Yep, well, I'll be screen sharing.
All right, go ahead.
Hello, can you hear me, Nikolai?
Yep.
Okay, cool. So hi everyone, I'm Max, and Alice,
Yeah.
does your mic
I'm
work?
Alice. Yeah, my mic is working.
Shuli?
And I'm Shule.
Okay, cool. So our project was about gaining access to a computer using a USB device, and we were inspired by kind of the likes of Mr. Robot and these other shows where people just go in and stick a USB stick into the computer and then do all sorts of crazy things. And so Alice is going to first talk about the attack overview and our threat model. I'm going to walk you guys through some of the hardware and software setup required, as well as a demo, and then Shuli is going to talk through the results and some discussions.
Yeah, so our overall goal for the project was to implement a malicious USB attack, sort of to explore the limitations and possibilities for this type of attack. And when it comes to USB attacks, there are sort of three categories that people have worked with so far. And one is where you just have like malicious code on the USB, someone finds it, picks it up, and opens the code on their device, and then something bad happens. There's a case where it's more of like a social engineering attack where there's a file on the USB once again, and it's like a phishing website or something like that where the user has to enter their password. And probably the more complicated attack is a HID type, which stands for Human Interface Device. And this is where the USB basically acts as a keyboard and can inject keystrokes and open the terminal and run a malicious script automatically. And so this is the attack that we focused on implementing. And you can see on the screen sort of an overview of the attack that we launched. So we have a USB type device that's capable of HID spoofing, so acts as a keyboard and can inject keystrokes. As a proof of concept, we had this malicious script that it injects that allows the victim's device pretty much to communicate with this FTP server that we have set up. And now it can upload and download files from the server, which opens a lot of possibilities for bad outcomes for the victim. For example, the attacker can upload the victim's files to the server, sensitive information, different data from their device. And they can also download files from the server, which could be custom attacks and different malicious scripts once again. And if we can go to the next slide, I'll talk about the threat model. Yeah, so based on what I described as the attack in the attack overview, we have sort of two sides to our threat model. In one case, the attacker has physical access to an unlocked and unattended computer. That means it's like in a workspace, or you're working in like stud 5 and you see someone went to the bathroom but left their laptop out. You can walk over, quickly plug in the USB. It'll automatically inject the payload. You'll unplug it and walk away. And that would pretty much be the whole attack. And the other case is where you leave this USB somewhere and someone finds it and plugs it in. They don't have to do anything beyond that, like opening the file or typing in their password or anything like that. And actually, this is more common than you might think. We found a study from, I believe, UIUC, where a researcher put out over 200 USBs, and almost 50 were plugged in by students or various people on the campus. So people will actually pick up these malicious USBs and plug them in unknowingly. And so I'm going to talk a little bit about how we actually set up the script and server in the next slide, just to give you an idea of the implementation of our attack. We set up an FTP server on a VM using Google Compute Engine, And there was a lot of sort of toggling the network rules and credentials for the connection, because we wanted the script to have basically credentials to log into the server rather than just having anyone be able to read and write from the server. And we wrote a script for both PowerShell and Bash to upload and download files from the server. And I have like a snippet of the code on the right. Max will talk about the USB setup now.
Yeah, so thanks, Alice. So in order to get a USB that could actually do this, we had to do some shopping and some experimentation with different types of USBs. We found out the hard way that actually most Raspberry Pis, and in fact, the ESP32, which is actually the free USB you get if you take the embedded systems class, does not have the capability to inject scripts. And so what we ended up using was the Raspberry Pi Zero, which is a $20 device you can buy off Amazon. And you can install, it's basically a small single board computer, and it has this vital HID, input output hardware. And once I got that, or once we got that, we looked online we had to create we had to install an operating system in order to actually use the computer. And the default for Raspberry Pis is Raspbian, but we ended up using Kali Linux, which is an open source kind of security operating system that a lot of penetration testers use, mainly so that we could more easily use this library for keystroke injection. And yeah, we were fortunate to find an open source library called PonP1. It's actually PonP1 ALOA, and it basically handles a lot of the interfacing with the computer, so that you can effectively just type a script. You can just call a bash script that you've written, and that'll make your computer execute it. So yeah, without further ado, here is our demo, and you guys can see what it actually does. Okay, so yeah, that was a demo of it working end to end. One of the use cases where someone would actually come in and plug in the USB. Yeah, hope you guys enjoyed that demo. And now I'm going to hand you over to Shule to talk a little bit about the different dependencies and what we took away from this project.
Okay, so one challenge with this attack was actually configuring the USB as a keyboard without any user input after plugging it in. And we saw that on Windows, it wasn't that difficult. So for a USB configuration, an OS needs to know some information about the device, such as the device class, subclass, vendor number, product number, etc. And we found that on Windows, none of these USB descriptor information fields mattered. We just like set those values to arbitrary values, and our device was able to inject scripts with random values in these fields. But on macOS, this method didn't work as easily. More specifically, when we plugged in the USB, a keyboard assistant dialog box would appear as shown here. and it would ask the user to configure the keyboard by pressing certain unidentified keys on the Mac keyboard. Since this wasn't feasible to do quickly using our setup, we had to find a workaround it. So to circumvent this dialog box, we set the vendor ID equal to Apple vendor ID and the product ID to be equal to Magic Keyboard A1644. And we found these numbers online on a USB ID repository, which wasn't that hard to find. And using these values, we were able to run the keystroke injection attack on a 2014 MacBook Pro, running the most recent Catalina. So in conclusion, we showed with this project that a malicious USB can be dangerous. It can send sensitive information to an attacker, hijack running processes on a machine, and do all kinds of exploits. And this is because the USB protocol is designed to be self-configuring, which makes the use extremely inconvenient, but allows such attacks to succeed. So the basic solution would be the operating system defending against these kind of attacks by improving how new USB connections are handled. And one simple suggestion we can make is similar to the Mac Keyboard Assistant dialog box, ask user a secret such as a password every time a new keyboard is connected. So this concludes our presentation, and we can now take any questions you have.
Yeah, and we'd just like to thank briefly Franz and Nikolai for giving us some helpful advice on looking more into USB PIDs and stuff like that. Yeah. Okay.
Cool. Yeah. Thanks very much. What do you guys think about how do you authenticate USB devices? I guess for keyboards, this kind of works if you're willing to type something on a keyboard every time you plug it in. Does this work for all the devices, or how would this work for other kinds of devices that you might worry about?
So if you care about this kind of attack that we're doing with HID inputs, then you can detect, it's basically, if it works for keyboards, then it works for this attack that we're concerned with. It's harder to protect against things like having a normal USB stick with a malicious file that someone will click and open. I think that's like a social engineering attack. It's very hard to protect against, but I think that broadly prompting a password would work if be fairly inconvenient for these kinds of USB keyboard injection attacks. Yeah.
Any other questions from others?
Oh, okay, hold on. How does the USB steal the password? Oh, okay, so Katalia asks how the USB steals the password. Okay, so the password, I mean, in this case, we're assuming that someone has stored their password on some file. I mean, it doesn't have to be an actual password. So this is kind of a stylized example. Really, it was just supposed to show that you can upload any file that the attacker can select in advance. And that might include having a function that can scan through all the user's files and just selecting ones that look particularly sensitive, maybe certain PNGs and all images or whatever. But yeah, so the file that we actually uploaded was just a file on the desktop that was called file.txt. And so that's just supposed to show that you can do that. And we could also make it so that the FTP, so we could download a keylogger from the FTP and install it locally as well. That's an alternative, but we didn't do that in the demo. Yeah.
All right, thanks very much. So next up we have Kazi talking about ARM binaries.
Hello. Yeah, hold on, let me share my screen. You guys see that?
Yep.
All right, so my project was on patching ARM binaries to detour execution. And this is a type of binary instrumentation. And this is basically when you try to modify the behavior of an executable without the source code. So this is difficult because usually when you, so you don't have the source code, so that means you're modifying the assembly directly. So you have to be worried about like how you're going to push around all the other addresses when you're adding in new instructions or when you're removing instructions. It's gonna kind of like shift everything around in memory, so you have to take account of that. And usually binary instrumentation is used in things such as address sanitizing. So this is when you add in checks to, you add in like memory checks that basically like asserts that cause the program to fail when something's out of bounds. This is used when you're like fuzzing to help you find bugs. You might also want to use instrumentation to patch bugs in commercial like or proprietary like binaries that you don't have the source code for. So dynamic instrumentation is when you're instrumenting a binary while like during runtime, and some tools for this include Intel Pin and Dynamo Rio. But my project is a static instrumentation, and there's some other previous attempts at this, such as Rambler, where they try to identify symbols in the code. And this is difficult because if you're compiling a binary without debug symbols, you don't really have like any labels in the code. You kind of just have to like brute force or like sort of guess at what the symbols are in order to disassemble it properly. Another tool called RetroWrite uses relocation data from position independent code and generates reassemblable assembly. And this can't handle like this doesn't work because not all code is going to be position independent. And lastly, there was a tool called Multiverse that I looked at, and they basically, their approach works, and I sort of adopted their approach. And the thing is, they have like a huge space overhead because since they're instrumenting x86, and x86 is a variable length instruction set, you kind of have to try like a brute force strategy to figure out what are all the possible ways you can disassemble a binary. So my objective in particular was to insert hooks into any ARM ELF binary to print out unique strings. The reason why I picked ARM is because all the instructions are fixed length, so I can basically patch out one instruction and put like a jump to like injected code. My steps were exactly this. I identified the most frequent instructions. I replaced the instruction with the branch and link that detoured execution. And then the injected code set up the args to a printf call using the link register. And then I return execution to original code. The reason why I decided to use this, the reason why I decided to insert like print statements is because if you had unique strings printed out at every function of a binary, you can determine a unique path through the control flow graph. And this will let you sort of like, it's going to help you reverse engineer a binary. Like let's say you had like an ARM firmware and you instrumented it with these with these print strings, and all these strings are output to a file. You can compare like the order of the strings to figure out like what functions were called and in what order. And this is useful because in like IoT devices you have like all these interrupts and stuff, and it's really difficult like to statically determine like how a firmware is supposed to like what happens during boot up or something like that. So my first step was to identify like instructions to patch out. And I did this using Ghidra's headless API because I was basically trying to find what the most frequent instruction is in the first basic blocks of all the functions in the binary. And Ghidra had a pretty good API for doing this. I also could have just taken the most frequent instructions in the entire binary, but if we got the most frequent instructions in the first basic block, we know that function definitely got called because the first basic block will always execute. Working with Ghidra's API was pretty confusing because there's like a lot of like roundabout ways of doing things, but this is an example of some code that gets the first basic block, then it constructs a histogram of like frequent instructions. This is my subject binary. I basically just a simple C program with 3 functions. When you compile it and run it, this is what it looks like. And these are the top 3 instructions in this binary. And so this is what my injected code looks like for this binary in particular. So there's kind of a lot going on here, but this first part is basically just setting up the arguments to printf and then calling printf. And one thing I also do is, so assume we just hit like I replaced an instruction with the branch and link to this injected section, and now the address of the instruction that we're going to return to is in the link register. So we use this link register to look up the instruction that we should have executed, but we didn't. And I do this by also cloning the original text section, and I inject this along with my injected code. And then I sort of use an offset to that clone text section to perform this lookup. And this works pretty well. And the reason why I did this is because, remember, we want to instrument multiple addresses for one instruction, because otherwise there would be like a big space overhead. It would be linear to how many instructions that we're patching out. But the way I did it is, if you have like one instruction and it appears in multiple places in the binary, you basically just need one entry in the jump table. So the way I return execution is I use this jump table, and it basically just compares so here I took these 2 frequent instructions and I put them here. So this is like one tap point, this is another tap point, and it basically compares. So using that clone text section from before, we compare the instruction that we were supposed to execute with the instruction in that entry of the table, and if it's equal to that, then we restore our registers, and then we perform that instruction, and then we go back to where it was supposed to execute at. And I wrote a script that generates these inject assembly files, and all you need to do is give it the JSON from before, from the Geetra script, and a number of tap points that you want to instrument. And the next step was to add a new section to the L file. So once you compile that assembly that I just showed you, and you extract the program code from it, so like the bytes from the text section, you dump that using object copy. I also dumped the original text section of the binary, and then I combined them into one binary, and then I injected it into the binary. And I used a tool called elf-inject, and this basically just like changes up the program headers of the elf file so that there's a new section and it gets properly loaded into virtual memory. So this means that we can like jump to it and like actually see it in GDB and stuff. And then the last step is to replace all instances of our tap points with the branch and link to our injected section. And I did this using a tool called Pwn Tools, which is really helpful because it lets you basically does easy conversion between virtual offsets and physical offsets. And one other thing I also had to do was parse the binary's PLT table, because when a binary is running, it loads dynamic symbols through something called lazy binding. And basically, the first time you call a function like printf, it doesn't have the address of printf in memory yet. So it does it goes through the PLT, and then this goes through something called the global offset table. And then it figures out the correct address, then it puts it there, and then it uses that. So in my injected code, I didn't, basically the printf in my injected code isn't the proper address when I inject it. So I need to patch it afterwards with the correct PLT entry. And once I did this, printf was working fine. And then the third thing that I had to patch was the offset between the original and the clone text section that I talked about before. Then I patch its placeholder. So over here, I basically put it at the top. So it's all ones, but then I rewrite it to the actual offset later, and that seemed to work fine. I had to calculate the relative jump by using, so I looked at the ARM documentation, and branch and link encodes a 24-bit immediate as the number you would jump to the PC. So this is how I calculated that, and it seemed to work fine. So these are my results. With one tap point, we see that instrumentation works, 2 tap points also works. Some weird like new lines getting added, but it works. 3 tap points works, but then once we reach 5 tap points, it doesn't work anymore, and like it seems to hang a bit. And after looking around, what happened was the codes tried to patch like GCC's setup and teardown functions. So these are like the functions that are called before main and the functions that are called after your program exits. And in particular, the link register was being computed on for some reason. And I should have seen this coming, but like my code currently overwrites the previous link register. So this means that execution is returned with violated assumptions. And I should have like thought about this from the beginning by patching double instructions instead of single instructions, because then I could have just done push LR and then branch and link. And then when I return execution, I would pop the LR and then I would basically just do the same thing. But I didn't really have time to go back and refactor my code for all this. But yeah, so these are the next steps to implement double instruction patching. So the link register is saved. I also need to ensure that I don't patch addresses in the setup and teardown functions. So this means I need to parse these sections of the binary for the function pointers. And then I also need to improve my instruction whitelist and register blacklist, because currently when I'm looking for instructions to patch out, I make sure that they're safe instructions by checking if the instruction is one of these. So we're not doing like anything weird with the stack or any like jumping or whatever. But yeah, that's all I have.
One question is, if you do double instruction patching, then how do you deal with indirect jumps that go to the middle of your double instruction?
Wait, what do you mean by that?
So if you're gonna detour pairs of instructions, like 2 instructions at a time,
Mm-hmm.
then the rest of the application code might jump into the middle of that pair, or like it would have jumped to the middle of the pair that was there before.
Oh, I see what you're saying. Like when you return execution, you would go back to
yeah, like you might accidentally pick a pair of instructions to patch where the rest of the application sometimes jumps into the middle of that sequence. Like you didn't know this because you're just doing binary instrumentation, right? So, but it turns out that sometimes at runtime you get an indirect computed jump to the middle of that. The reason I'm thinking computed is because for direct jumps, maybe you could find them statically. But if you have like an indirect jump through like a value address, then you might not know whether that push LR instruction ever ran.
Oh, I see what you're saying.
Misalign the stack.
Yeah. Sort of need to think about this a bit more then, I guess. But I feel like what I had was like working pretty fine, and maybe like adding a couple of restrictions and like, sort of testing it out a bit more. I could probably figure out all the edge cases, but I don't know. This is kind of fun to explore.
Yeah, cool stuff. Yeah, thanks very much. I guess, yeah, I was thinking like actually this double instruction patching almost gives up the reason you chose ARM in the first place, where you said, oh, ARM is great because we have fixed size instructions. Anyway, yeah. All right, thanks very much. I guess to make sure we wrap up on time, we should move on. So next up we have Felipe, who's going to talk about Jibo security. Go ahead, man.
Oh. Hi, Nikolai. Sure, let me share my screen. Okay, can you all see?
Yes.
Okay, awesome. So yes, let me set the timer. So yes, my project is on Jibo security as a path to HIPAA compliance. So let's give you an overview of what is Jibo. Jibo was the originary social robot. It was developed by my PI. It was its company, and it shut down in 2018. So since then, my lab is one of the few organizations that keeps doing active research with the robot, and they provide maintenance in terms of functionality, not so much in terms of security. For me, I have personal interests in terms of the applications of the robot. I do medical applications of computer vision as my personal research. And so for me, it's interesting to see maybe what would it take to use the robot for medical applications, right? And so for that reason, I started looking into this stuff, right? The robot has some nice properties like a high-level SDK for development. So it has access to control, positioning, animations, and speech. And it has a nice personality and a cuteness factor, which is something quite interesting for research purposes and for long-term deployments, because you can get the robot and put it in people's homes and they end up loving the robot. They end up really complying and engaging in like useful, meaningful interactions. For me personally, I also have an interest in the robot because of its 360-degree view, because I do research in computer vision. And so all of these are some of the features. Also, another thing to keep in mind is that the robot was designed as one of the most secure IoT devices of the time. It's COPPA compliant, and COPPA is it's about the Council of Parent, Advocate, and Attorneys. It's for to secure children-generated content and for parents to be able to like take it down if they want to. And so it's a highly secure system, and my interest in my project was mostly on taking this system and figuring out what does it take to grab this system and use it for medical research. So let's talk a little bit about HIPAA. HIPAA is the set of rules and regulations that are used for medical research. And so I'll mention briefly, privacy rule is about medical stuff. So the kind of information that you're allowed to gather. There's the omnibus rule, which is more for about a business associate and you have to log information and notify breaches and all of that. And the security rule, which is what we care about in this project, is about protecting, information. Do I have a question?
I think your screen sharing might have done something a little bit funny. I think we see we don't see your full screen view. So maybe it's easiest if you just flip the slides in this view or something.
What do you see then?
I think right now we see a browser with several tabs and one tab open, which is your Google Sheets.
Okay, let me see this then. Oh, I'm sorry.
Oh yeah, there we go. Yeah, yep, thanks.
Okay, better? Sorry. And so we have the security rule, which is mostly about what we care about, which is that medical people who should have access to medical information are the only people who will have access to that information. And so that takes on different, that have to be handled at the administrative level, but also at the technical level. And for the technical purposes, we have 3 main goals, which is encryption of information at rest, encryption of information over the network, so in transit, and proper key management. So let's dive into the technicals. So the security of the system, to put up this security assessment of the system, I had to read through technical documents, and these were about how the system was designed to be, which was actually quite different from what it turned out to be implemented. So I had to also set up my own systems, compile my own images, and set up the clouds and all of this, and actually interview engineers to figure out the full picture of the model. So the system is based on 2 components. One is the robot, which is an embedded Linux system, and a cloud instance, and a set of microservices that run on both and communicate with each other. So let's first take a look at the robot architecture. The image was made, the image is a compiled Linux image using Buildroot. Buildroot is a cross-compiler for Linux embedded systems. So you can make a Linux image for something like Raspberry Pi as well. And it's got a nice property that all of the packages that are downloaded before they're compiled, they are matched against checksum, so they have integrity checks, which is really good. The next step that we do to set up the robot is to flash it. So we get that compiled image and we put it in the robot. For that purpose, the robot has to be set to recovery mode, which means that it basically becomes a thumb drive and you can read or write to it through a physical cable. But this is only true if you possess the developer key, which is a highly regarded secret. In any case, we cannot still assume we should still assume that an adversary could get access to this key. And for that reason, we need to secure the system. We need to, for HIPAA compliance, my suggestion for this is to encrypt the file system in a schema where during compilation, grab a symmetric key, we encrypt the file system, we toss away the key, no one has access to the file system. We'll see later that all of the medical information and useful stuff can be loaded in the cloud, stored there safely, and for that reason, no one needs access to the robot's file system. We can be more secure and certain that it's better to just have a black box, lock it down, and secure it. And so the next step in setting up a robot is to get the credentials in there. So after it's flashed, it's set to something called developer mode, which is like a highly insecure state. But at this point, the robot's still not connected to any network, so that's fine. A researcher can ping or call one of the services running in the cloud, which we'll talk about it in a minute. Create an account, register a robot, and then download credentials, put it in the robot, point the robot to the cloud, and then we are able to secure it for deployment. We set up a firewall, we close all of the ports. We only allow TCP ports. So even the researchers are locked out of the robot. And at this point, we're ready for deployment. So after that, then we can go ahead and connect to the network and it'll talk to the server. So some of our risks that we assess at this point is one, compromised credential. We'll mention that in a minute. Two is that build root and the cross compiler tool. It actually fits in time and it hasn't been updated in many years. So the next step for achieving good security is to update all of these packages and apply security patches. These are very important. So let's move on to the cloud service. So now we have the robot that was set up to connect to this cloud. The cloud itself is a set of Linux microservices, all containerized with a firewall set to connect to talk to each other for port rules. And these are containerized for fault isolation. We have one service, which is called the hub, which is the one that binds to the TCP port. And it redirects traffic to the microservices. It, in fact, also validates credentials of the incoming requests. So only a robot can actually, let me see, question? Okay, yes, okay. So yes, we have, so for HIPAA compliance, one of our goals we set was security of information in transit. So HTTPS and WebSockets, secure WebSockets are used for communication over the network. We use HTTP and WebSockets between interconnections of services, which is fine for purposes because they all live inside the same instance. Now that brings us to one of our risks, which is a memory dump attack. We don't concern too much about malware doing this attack, but more about maybe Amazon or AWS doing a memory dump for metric purposes. And for that reason, we have to sign an agreement. In terms of storage, it's quite an interesting story, and this is how we get to the compromised credentials, because we store in the server user-generated content. So all of this content, like databases that live in the server and pictures that the user can take, all of them are encrypted in the robot by a user-generated content key, which lives only in the robot, and no one has access to this key. So the robot is actually storing all of this stuff in the cloud as backups, and they live in the server. A compromised credential could allow an adversary to make valid requests to the server, so they could actually get and corrupt data in the server. But we don't. But in our security model, we are still able to keep secure all of the user-generated data, which is really important for medical applications, because all of the data that is generated by the user is stored encrypted in the server. So if an adversary gets a hold of compromised credentials, they could get a hold of the user-generated content, but this would be encrypted and protected for that reason, for our purposes. In future work, well, I'll try to wrap it up because I'm running out of time, but in future work, we still need to take a look at the different databases that live in the cloud, because there's also MongoDB databases that are unencrypted, which might be storing some de-anonymizable information in the logs. It's important for us to be able to tell if this contains any user information. And okay, so this is like a standard web architecture for HIPAA. I'll just mention that there is logs of all of the, that it's important to have like audit logs of all of the requests that go into the server, of all of the configuration changes and all of the permissions that are set. These should all be audited for the purpose of a medical application. That there's a production virtual private cloud and the development one, and clients talk to the production one. So I'll try to wrap it up since I'm running out of time. But for next steps is that, well, in this project, we set up a security model and all of the risks and potential fixes for this. So the next steps would be to actually go through the system and implement these different security metrics. So for next steps, we have to apply security patches to the robot images. We have to encrypt the file system. We have to inspect these different databases. And it would be really nice to actually take a look at code coverage of the different services that are proprietary services that run there in the system. Make sure that they're implemented correctly, so particularly those that validate requests over the network. So I'll wrap it up. Thank you, everyone. I'll take questions at this point. Any questions? Okay, so thank you. Thank you, everybody.
Thanks very much. Yeah, so last up, we have Jeff and Daniel talking about autonomous vehicle controls.
Jeff, can you share screen?
Yeah, hello. I think you have to stop sharing.
Oh yeah, Felipe, can you unshare your screen? That might help us.
Okay, can everyone see this?
Yep, looks good.
All right, so our project is about security and autonomous vehicle control. So more and more people are using self-driving cars each year, and there needs to be a good fail-safe for these vehicles, because like one mistake can be potentially pretty bad. And currently many autonomous vehicles use complex processing and machine learning for stuff like perception and planning. And an important thing is that we need a runtime monitor that's simple and easy to verify.
So what is a runtime monitor? So a typical runtime monitor is basically the last line of defense that performs a safety check for the car. So here is the architecture for a typical runtime monitor system, in which the monitor takes the sensor data, and it basically uses the sensor data to determine if the state the vehicle is in is safe, and whether or not the proposed action given from the controller of the car is safe. So the monitor has to do its own perception, and often this leads to the monitor being just as complicated as the controller in a self-driving car. So we decided to use a certified control monitor, which is a new safety architecture. And in here, the monitor, instead of taking sensor data, it takes a certificate from the controller. And this is basically the controller sending the monitor proof that the current state of the car is safe and that the proposed action is safe. And this allows the monitor to be much simpler, because instead of having to do all of its own perception, it is allowing the controller to do the work, and the controller is basically finding the solution to the perception problem, and then the monitor is checking that solution. And from here, the monitor then determines whether or not the chosen action is safe, and it communicates that with the actuators which actually move the car. And our controller specifically for the project identifies lane lines in the image, and the monitor checks if, one, the lane lines are reasonably parallel and spaced apart, and two, whether or not there are white or yellow bands at the proposed lane lines on the image. So for our threat model, we assume that the controller is malicious. So this means that it can basically send whatever it wants to the monitor, and it can try to tamper with the sensor data or try to otherwise convince the monitor that everything is okay when in fact it isn't. So the reason we assume the controller is malicious is because it is by far the most complicated piece of software in self-driving cars. And for example, you can imagine an attacker might exploit a buffer overflow through some internet connected component in the controller, and this would allow the attacker to basically gain full control of the controller and allow it to send whatever it wants to the monitor. And and we also assume all other components are trusted because they are simpler and not exposed to any outside communication. So basically, we are trying to isolate the different components from each other so that a malicious controller cannot affect the other components, and also try to verify that the sensor data is in fact legitimate.
So in our version of certified control, we split entire design into 4 components: the sensor, the controller, the monitor, and the actuators. So the sensor is the one that basically takes images from the dash cam and then timestamp/signs it. By signing, I mean like encrypting the image and timestamp combined, like as a string. And that sends those 3 pieces of information to the controller. And a normal controller would just detect lane lines and pass that information along with the sensor data to the monitor. Like a malicious one might change stuff, but the monitor is there to check if the image came from the sensor. So if the signature makes sense, and if the controller is doing its job, like if the controller's proposed lane lines match the sensor's image, basically. And then monitor will tell the actuator to continue or stop. If they say stop, then the actuator will apply the emergency brakes. And our model is split into, so each square represents a Docker container, and each green line represents a Docker bridge network. So how does the monitor verify that the controller doesn't like mess with anything? So at the beginning on car startup, the sensor generates a private and public key. The sensor keeps the private key and then sends the public key directly to the monitor for use. So each time the sensor wants to send the image to the controller, they would, like I said before, concatenate the image and the timestamp and hash it using SHA-512, and then encrypt it with a private key using RSA. And then the controller shouldn't touch it. But if it does, the monitor will find out, because the monitor will decrypt the signature to get the hash back, and then the monitor will create the hash from the image and timestamp itself to see if it matches.
So for isolation, we used software called Docker, and it's very similar to LXC. It also provides isolation in the form of containers that use OS level virtualization. And we use Docker because it's really flexible and pretty simple to use. And for isolation of networks and communication, we used custom bridge networks, and this allowed each container to get a different IP address for each network it was a part of. So going back to this diagram, the sensor container would have a different IP address for communicating on the signed images network than for the public key network. And this just enforced isolation between networks. and we got to define what networks each container was a part of. So in order to deploy multiple containers, we use Docker Compose, and this also allowed us to synchronize the clocks for different containers. So recall that the sensor timestamps the image and the monitor checks if the timestamp is reasonable. So for this to work, we had to synchronize the clocks, and this allowed those containers to basically take the clock from the host machine and use that.
So to test our code, we created 4 incorrect controllers. So the first 3 are malicious. The first one sends a different image from what the sensor sends the controller. So maybe from the hacker's laptop or something. The second one sends the malicious controller might decide to delay the image for 2 seconds, hoping it would crash. Or they can just stop sending certificates altogether to the monitor. And the fourth incorrect controller is just supposed to be poor performing, like proposing incorrect lane lines given the sensor image. And we noticed that Docker does slow things down a little. So to improve performance, we have the sensor also send a decreased resolution version of the image. That way the controller uses the full resolution image and the monitor checks using the low resolution version to make it a lot faster. And the end result is 0.4 seconds per image.
And correctly in all 4 bad controllers, the monitor correctly intervenes and says that something is wrong. And we're going to do a demo. So here, I'll just run the original controller, and the Docker Compose is starting up. And as you can see in the beginning, there's a one-time key exchange between the sensor and the monitor. And then after that, everything starts, and the monitor is saying the images it receives are legitimate and the timestamps are okay. And also that the probes lane lines seem to match the image. And if I change the controller in the that's being used by the system, so I'll change it to one that tries to tamper with the image. And if I try to run it again, then once again, it's running Docker Compose, and there's a key generation. And it says to stop because the image was tampered with. So our system correctly identifies when the image is being tampered with. And for the sake of time, we're only going to do this example. And yeah, that's our self-driving car security project. Are there any questions?
You got some question in the chat from Max asking what kind of security autonomous vehicles systems have now, if any.
So a lot of it is very experimental, and it's sort of going back to the slide here. It's sort of more on the left side, on the left diagram. So the monitor, if it tries to do enforce strong security, then it will actually do its own perception itself. And this basically, this works in a lot of situations, but it leads to the monitor just being as complex as the controller. So it doesn't actually create a verifiable trusted base.
All right, thanks very much. So we're running a little bit late, so thanks for everyone that presented, and thanks for all of you guys for sticking with this class, even though we've been lecturing remotely. It's been great to have you all participating and asking questions online. So don't forget to submit all the project reports and your lab 5s, and I guess we'll see you guys for the final exam virtually, so to say. That'll be next week. If you guys have any questions, I'm happy to take any sort of questions now, but otherwise, thanks very much. We've enjoyed having you in the class. All right. Well, in that case, take care and good luck with the final.